Welcome to our geometric distributions video, where we will cover all things regarding geometric distributions. Assuming you are already familiar with geometric distributions, this video should serve as a helpful review. If you have no idea what a geometric distribution is, well, hopefully this video will assist you in understanding them. Get ready, because it's going to be an extremely informative guide to geometric distributions.
Let's dive into the properties of geometric distributions. The first one to note is that geometric distributions are mutually exclusive. This means events cannot occur at the same time, and that the result will either come out as a success or failure. We can also identify this as independent trials, meaning that the likelihood of each possible outcome does not change from trial to trial, and that the probability of success is the same for all trials. For our geometric random variable, we'll use x to represent the number of trials until the first success is observed. Don't forget that the success is included. An example of how a geometric distribution question might be asked could be, if your probability of success is 0.2, what is the probability you will meet an independent voter on your third try? Now let's look at our probability formula for geometric distributions. Let P represent the constant probability that any trial results in a success. Our formula is P of x is equal to P times 1 minus P to the power of x minus 1, where x could be 1, 2, 3, and on. Remember, there is not a fixed number of trials in geometric distributions.
Now let's move on to calculator functions. There are a few important graphing calculator functions to remember when working with geometric functions. The first one we'll go over is geomet_PDF. This function finds the geometric probability that a geometric random variable is equal to an exact value. Use this function when you need to find the probability of a first observed success at an exact value of trials, that being x. The second function we'll go over is geomet_CDF. This function finds the cumulative geometric probability that a geometric random variable is less than or equal to a value. Use this function when you need to find the probability that it takes at most a specific amount of trials, that being x, to get a success. Now let's move on to the important formulas to remember. There are two critical formulas to remember when working with geometric distributions, with those formulas being for the mean and standard deviation of the distribution. Let P represent the probability of obtaining a success. The formula for the mean of a geometric distribution is 1 divided by P, or the probability of success. The formula for the standard deviation of a geometric distribution is the square root of 1 minus P, the probability of success, divided by P squared. It's critical that you remember these formulas or have them on hand when working with geometric distributions.
Okay, so geometric and binomial distributions are two types of probability sequences. Even though they do share some similarities, such as mutual exclusive outcomes and independent trials, there are a few differences between them, the most defining one being the amount of trials. With binomial distributions, you have a fixed number of trials, meaning that you are given a set amount and you cannot go beyond that while counting how many successes are in that amount. With geometric distributions, it's a little bit different. You are given as many trials as possible until the first success happens. Keep in mind, the total number of trials also includes the first success as well. Think of it as a degrees of freedom situation where instead of n minus 1, you have n plus 1 instead. However, the differences don't stop at just the properties of the distributions, but the formulas of the distributions as well. The binomial probability formula has two variables, including n, which represents the number of independent trials in an experiment, and p representing the constant probability that of the success in a trial. And in the geometric probability formula, it's a little bit different. With that formula, it only really has n, which is the number of independent trials in the formula.
A certain basketball player has a 65% chance of making a free throw. Assume all free throws are independent. What is the probability that he makes a free throw on his third try? It takes him 2 or 3 tries to make his first free throw, or it takes him less than 5 attempts to make his first free throw. So for part A, we need to realize that the probability of success is 0.65, which is the probability that he makes a free throw successfully. And remember that the probability formula for a geometric distribution is p times 1 minus p to the power of x minus 1, where x is the number of trials until the first success. So the question asks the probability of making a free throw on the third try, so x equals 3. Using the formula, we get 0.65 times 0.35 squared, which is 0.079. Additionally, we could have used the calculator for this via Geomet PDF for using 0.65 as our probability and 3 as our number of trials. For part B, x can be 2 or 3, and since x can take on multiple values, the total probability of x being 2 or 3 is actually the sum of p equals x equals 2 and p of x equals 3. So for p of x equals 2, it's 0.65 times 0.35, which equals 0.2275, and p of x equals 3 is 0.65 times 0.35 squared, which is 0.079, and when you add those two up together, you get 0.307. Again, you could have used the calculator for this using 0.65 as your probability and 2 or 3 as your number of trials, and you get the same result either way. For part C, we need to keep in mind that the problem says less than 5 throws. So in this case, x equals 4 because that's the closest number to 5, but not exactly 5. So for this, it's a cumulative probability. So we use Geomet CDF, 0.65 as our probability again, and 4 as our number of trials, and we get 0.985. In example 2, 80% of all business startups report that they generate a profit in their first year. If we take a sample of 10 of these business startups, find the probability that exactly 7 will generate a profit in their first year. Now, is this a geometric problem? The answer is no, because there's actually a fixed number of trials, which is not part of geometric, but actually binomial.
Thank you for watching our educational and informal video on geometric distributions. If you didn't already know what geometric distributions were, we hope you do now. Thank you for watching.